Morning everyone. Welcome to the Tuesday refresher with EasyPower. I'm Jim Chastain in the Sales and Marketing Group, and today's topic is a follow-up to a session we did early last month on selective device coordination. We ran out of time, and so we're going to be following that up with the refresher topic today. Welcome everyone, and let's start with our first refresher poll question, and that is, what type of issues do you have most problems with in terms of coordination? So here's a multiple choice to kind of give people some opportunity to give us feedback. Let us know kind of what vexes you most. And the subject is broad enough that we can't cover it even in a 1-hour session, and so I'm planning to sparse out the different segments and applications and focus a little bit more on the future based upon some of this feedback. So I appreciate your participation. So here's what folks are telling us. It looks like differential relays are probably the most problematic. So we're going to, as I say, touch on that today, and certainly we will follow up in the future with more specifics. Last week's refresher, we did a session on custom templates for panel schedules. A couple questions came up regarding utilizing the arc flash analysis results or assessment results and putting them in the template. Specifically, fault and store allows us to put the arc flash data in the panel schedule. So the question is, if you have multiple scenarios for the system, what data is stored? And the answer is whatever scenario is in effect at the time will be loaded into the panels that are part of the study. So the question, and the same question came up as far as the date of the template. The date and time variable actually records the specific time that the analysis was done. And if you want to have a fixed time, then you might not want to use that variable. You might want to use a fixed text entry to fill in the blank for those panels. And if you want to go back and just take the worst case scenario for each panel, and you've got multiple panels that can be the worst case, the way to do that would be to set up the scenario and just fault that one panel to load and store, and so it will be updated, and none of the other panels that may not necessarily be the worst case in that scenario would be updated. So if you got more questions on that, by all means, you're welcome to contact us, Jim at EasyPower.com or tech support at EasyPower.com, and we can help with your specific requirements. So as I mentioned, last month we spent an hour on selective coordination. We covered maintenance mode, zone selective interlocking, relay controlled fuses, and we ran out of time. Today we're going to start with differential relays and then breeze through arc flash relays, emphasize sequence of events, and another differential relay application is the generator voltage restraint relay, and then cover a little bit the DC side of the world, and hopefully it won't overrun our time slot. So let me jump into the tools and let's talk about that starting right now. I like to re-emphasize the fact that from this start page you have access to the user's guide, and as it pertains to the subject today, one thing about the way that this is set up as a PDF is that you go in and search on, I didn't want to print, I want to search. I can go in and search on relays and find specific topics to see what the references are. And so in this particular case, if we were just to go in and look at relays, you'd see that we have some 60, a couple hundred references. And if we just scroll through those, you'll notice that it gives us a wide variety of data, and not the least of which is how to set up and edit the relay itself, the symbol itself, and how to utilize it in specific applications. So I'd encourage you, by all means, to use the user's guide, and if you got questions beyond that, please contact tech support and we can help you out. All right, so the first example we're going to start with is the differential relays. So let's kind of bring that on. And what you'll notice here is that we kind of have overlapping effects. So in this particular one line, we have the individual overcurrent relays for the individual lines, so the main coming in and each of the feeders. And as we set these up, these will give us a trip of, in this case, the main breaker if we have an overcurrent detected on the main line coming in. Likewise, if we have overcurrent on any of the outgoing feeders, it can isolate that individual feeder. So the purpose of a differential relay is to protect a specific piece of gear like a transformer, a major transformer, or in this case the switch gear. And what it does, rather than look at any single circuit, is it will compare the, in effect, null out the standard currents for the system that are normal. So it depends upon the way the CTs are connected, and in some cases the way that the relay is connected. But in essence, what this will do is compare the incoming current with the total of the outgoing current, and as long as they stay within a specific range, then this relay doesn't do anything. But as soon as, and so it's effectively they null out the totals against each other. And so this relay can be very sensitive to any discrepancy that's outside of that range. And so that saves or protects the switchgear from things like an arc flash or from accidental faults that may not necessarily be isolated to any particular leg. So the point being is if we go to short circuit and we fault this particular bus, and let's look at the current, and we range it for arc flash, we see that the way this is set up is that R5 has tripped based upon this fault. And while that's what we want to happen, as long as we knew this was the faulting device or the faulting circuit, that would be acceptable operation, but it doesn't protect this whole zone that we're concerned about or concerned with. And as I say, this can include a transformer or even multiple transformers based upon how we've designed our system. So the way this is handled as far as providing the settings of the differential relay, and this is the one that we want to trip, that we want to sense the fault as well. If we go in and look at this, the way that this relay is set up, on the settings tab, we see that it's set up for a device function of 87, which is a differential. And it's primarily set up for a fixed response time-wise. And the setting here, as I say, is one of differential, and it has really nothing to do with the absolute current through the bus itself in normal operations. So where this is set up in EasyPower is when we go to the individual bus and open up the dialog box, we see that in this case we want to make sure this is a switchgear bus, that the arc flash hazard tab gives us the ability to override the global options. And in this case we're specifically looking at a response from this relay for a fixed amount of time. And so what we do is, in this case, because we do want to respond to the other TCC, we're going to set up a user-defined time as well as the TCC times. And so the upstream device here will be differential, so we can verify that which fault it's responding to. The relay function will be the normal 87, and this relay is specified to respond to the differential response of 0.15. And so we're going to make that the maximum time of a fault on this bus if this is the relay that's invoked it. So we're going to apply this, go to short circuit focus, fault the buses, and let's go back and look at our arc flash. I just want to fault one bus. And so now we see if we have an overcurrent fault, R5 will trip normally and it'll be in this range. But if we see a differential fault, then the differential relay, and we can put in the R1 here, which is probably the way to do it. In fact, let's go back and make that more specific. Now, as I'm in short circuit, fault the bus, look at my fault options, we can see here on the main switchgear, we have both the calculations for the relay, which is phase overcurrent, or the incoming, and the differential R1, which would trip if we had a fault, and the difference in incident energy, and considerably different based upon the time difference. So that's the way, and so clearly we can't simulate that difference in the occurrence, but if we've properly connected and tested the relay per our one-line drawing, then this is the way we can simulate its response in the system. Now, same is true, a very similar setup is true when we're using a light-sensitive arc flash relay, because again, we can't simulate that in the tools. So here's what I've come up with, and the whole point is to document on my one line what my protective scheme is, so that other people can understand and or I remind myself when I get down the road. What I've done here is I'm using an ABB arc flash relay that has the ability to daisy chain a number of sensors, or they can be hooked up individually. The way I've got it hooked up right now is that everything is daisy chained, so there's no difference except for potentially a time lag between a downstream fault and an upstream fault. And this, if you go back to the information that the folks from ABB presented, this is essentially a function of the repeaters that pass along the fiber optic sensing and ultimately trigger the relay to open up the main breaker. So what we do is very similar in terms of the way we just did with differential. For our setup for the main bus, and I'm just worried about this case, the arc flash sensing, I'm going to use user-defined times, arc flash sensed AFD function, and we're setting this up for a 3-cycle response on the high voltage side. For the downstream feeders, same type of setup, except the time response may be a little bit different, just because they have to go through a couple other connections. And again, this is all based upon the specifications and the way that my hardware is hooked up. So at this point now, when we go into short circuit focus, we can fault any individual bus. We can look at the results. We see that we have an arc flash, they misspelled, sensed fault tripped by the AFD relay. And again, I probably want to put in my R1. But now, based upon the time of 83 milliseconds, my arc flash boundary and my incident energy are very respectable and reflect the extra added safety that you get from this type of a system. Now, you'll notice I used a relay and a CT, even though it's not indicated in the tripping, in the information that was supplied by the ABB folks. there's an option to have a relay sensed or a CT sensed current level that enables the function so that you don't start getting trips from light that's generated when you don't have the system on or you don't have a minimum amount of current. So at least for my application, that's the way I've done this. There are ways to kind of modify that, I think, based upon your need. All right, so again, what we're taking advantage of is the so the questions, guide reference book on how to learn doing relay settings, please. Yes, so a question from Zaid. We'll touch on that at the tail end. Okay, so in essence, what we're doing is taking advantage of the options in the EasyPower tools to override kind of the standard settings and customize the response of this particular bus to this type of a relay. Next question, next topic is, and I wanted to kind of emphasize this in part because in a complex system, I believe one of the more valuable utilities in the EasyPower tool suite is sequence of events. And the more complex, the more interconnected, the more back channels you have for current flow on current or faults, the more valuable the sequence of events is. So let me kind of walk through this real briefly, and I invite you to try it out a few times because it can save a lot of frustration trying to hunt down or modify a relay setting when it turns out that relay may or may not be the actual tripping device in the fault that you're describing. So here we have a typical radial system, and it's, like I say, it's the more complicated, the more interconnected we have, the more valuable this utility. If I pick out a particular bus, I want to be in my coordination focus. I'm going to look at current, and it doesn't matter which current. In this case, we're going to use half-cycle fault current. Fault the bus, and if I've done it correctly, which I didn't, I'm going to go back and fault just a single bus. Just double-click on the one I'm looking at. I've got my remote current showing and the voltage showing at each of these other buses, but this is the fault that's driving the fault current. By going through that procedure, I have the ability to illuminate or utilize the sequence of events icon here at the top, second row just to the right of the lightning bolt, and I can toggle the sequence of events, which gives me the trip of every device upstream of that particular, not just upstream, but of any place that's drawing current. So in this case, we see this breaker trip at 50 milliseconds, this breaker trip at 340 milliseconds. Here's a relay that trips at a second, a little over a second. Here's another one that doesn't trip, 1,000 seconds is what's indicated. And here's one that's tripping, indicated another 1,000 seconds. But the point, there's several points to be made. First of all, this would be nice to see on a tabular report, because in complex systems, this could be 15 different current paths that we're looking at. Under PDC options, I can, general, right-hand column, bottom, create sequence of events report. By clicking on this and then faulting that bus again, so I'm just going to double click on the single bus. Under my list of windows, I will have a sequence of events report. And now this will tell me essentially what each trip element in the system will respond and the trip current that it's going to see. The significance here is oftentimes an upstream device where we may be thinking it should be tripping, it may not see the amount of current that it would take, And in this particular case, what we're seeing is that the upstream relays aren't even getting close to getting the type of trip current, and so they really can't respond to that remote fault. On the other hand, if we got a fault on the main bus, you can see here now we have much higher current going to the upstream relays, and they in fact operate as we hoped. Okay, so that's called sequence of events. It's the procedure is specific, and that's why it's worth practicing. But I need to be in the coordination focus. I need to be in current. I want to pick out and fault a single bus and make sure I have my PDC options, create sequence of events report checked. Now with that done, I can fault the single bus, and it will give me, as I click on sequence of events, it will indicate both online, the trip settings, the tripping time for each upstream element, and under my Windows list, I will see that spelled out in detail. Okay, so then the last system we're going to look at is going to be the DC systems. So this is a little different in that it's somewhat limited by the type of devices that are available in the system. And so let me just kind of come up with what I've set up. Oh, before I go out there, I want to do my voltage restrained relay. There's another type of differential relay that's utilized when we have variable voltage, and very frequently this is used in a generator protection scheme. And what it amounts to here is when I go to short circuit and fault this particular bus downstream, I may end up with some sort of a fault condition that's dependent upon the variations in this settings because of the voltage sensitivity. So the point I want to show is once I fault this bus, the maximum, and so we're looking at voltage on remote by clicking on this VI, remote bus VI icon. We show that in this remote bus, the lowest voltage it'll get to is 277 volts, or 27 per U, 0.27 per U, excuse me, not volts. Well, it turns out that's about 25% of the maximum setting for the voltages. When I go in and look how this relay was set up, under its settings, it has the ability to have a time multiplier based upon a curve, and so rather than have it 100% for this relay, the maximum or the lowest voltage that a fault will show locally will be 25%, so the more accurate or correct setting will be a 25% ratio, which scales the voltage now that this relay is responding to. And when we go back to short circuit and fault the bus, and let's say we fault this individual bus, we still have the same current, the same voltage, but now in terms of incident energy, it's more responsive to the current and the time that it's going to trip for this downstream fault. And so that's how you deal with a voltage constraint relay for transformers, excuse me, for generators. Okay, let's get to DC. And here it comes down to one little note I want to make in terms of the model for a DC arc flash. IEEE does not have a recommendation. What generally the industry goes by is a recommendation that's located in NFPA 70E, informative appendix D, and paragraph D 5.1 talks about the calculation of incident energy for DC systems up to 1 kV. Basically, you take half of the bolted fault current as your arcing current, and then utilize this equation which incorporates the voltage, the arcing current, the time of the response, and the distance, working distance in centimeters. And then there's a note that if you're operating in an enclosure like a switchgear or connection box, that you want to multiply the results based upon incident energy being amplified in a constricted space. All right, so let's jump into EasyPower and show how this is dealt with. So here we have a DC system that's connected to an AC system through this rectifier, and we have a number of DC elements that are in the system. If we go into short circuit and fault the buses and look at incident energy, we can see that there's a number of values here, and likewise if we look at our arc flash hazard spreadsheet, we can see that switchgear B DC is responding to BL1, which is the first breaker upstream of it. So in terms of coordination, if we go to the coordination focus and fault a specific bus, for current, I'm going to do the same response for sequence of events. So as I toggle that, you can see that I have my trip settings, or the trip's time, for each upstream bus. And in this case, nothing's going beyond the rectifier. I can look at my reports, if I've generated a report, and it'll show me that I have some overlap between a couple of the upstream breakers. So the problem ends up being, or the fact of the matter is, when I go to look at any given leg of protective devices, so I'm going to highlight these bottom two legs and this breaker and this breaker and plot them, and go ahead and let's see if I got everything. Now if I fault, I didn't get all the breakers. Let's try this again. So I'm going to left click and drag, hold down Control and add this breaker, and the rectifier. See if we got them that time. All right, so the issue is there's not a lot of flexibility in the settings or the protective devices in the DC side of the world, and there's a particular problem when we have the arcing current that falls into the vertical band of that MCC, or the multi-decay circuit breaker. And when that's the case, the manufacturer doesn't guarantee the trip unit to respond until it reaches the top of that vertical band. So if I were to fault this particular bus, you can see that I limit the maximum current. I should see BL5, which is, where's BL5? BL5 is the brown one. And there is showing my arcing current for BL5. Actually, this is showing the arcing current for BL1. So BL1 is the one device in the system that has a guaranteed trip unit, because if I take each of these out, that's the one that's being used to calculate the incident energy, because my downstream devices aren't guaranteeing that they will clear in the time that I want. And so that's why I'm seeing the BL1 as being the protective device in this particular case. So the way I kind of isolate through this is I can pick out a specific unit. Let's take out BL1 and see what happens if I take it out of the system by not plotting its response. And let's take out BL2, do the same thing. So the question is, why isn't it calculating on the downstream breakers? And right here I can see that the answer is, even though BL5 is responding, the manufacturer doesn't guarantee it to clear until it gets to the top of this particular band, and so we can't utilize it as far as calculations. Now, whether or not BL5 is adjustable is the question, and if you go to look at this at a 400 amp breaker, that's all I'm going to get. I have some higher settings, which won't help the situation in terms of trying to move this vertical band to the left. So that's the way you set it up. I'm not sure if I have, unless I pick out different devices, and at that point what I would suggest is I go in and I try to utilize a new curve, and we can say try out a low voltage fuse that we could see if, well, would a fuse work better in this situation. And let's say we have a 350 amp load. So here's where my fuse response would be, and maybe that would be the better solution compared to a breaker that looks like this. The purpose of the tools is to give us more visibility of what's actually going on in the system, and at this point nothing's to say that there's anything wrong with this design, but if I want selectivity between this breaker and the upstream breakers, this particular scheme is not going to give it to me. So I have to make some decisions, and at that point we go through some what-if situations and make a decision as to what kind of isolation I need, how significant or how frequently this particular load is going to fault, and what the downside of pulling the whole system down, because effectively that's what it's going to do by opening up this breaker. Okay, so that was the information that I wanted to cover. Let me see if we got some questions that I can help with. Anything I can't answer online, be more than happy to get back to you, or you're welcome to contact tech support.